name's Adrian, and what I'm going to be doing today is I'm going to be doing a chi-square goodness of fit test to determine whether a company's claim that their M&M's distribution of colors is true. So in this scenario, we have a company, Mars Inc., right, who makes the M&Ms, and now they claim that this is the distribution of the different colors of the M&Ms that they offer. Now in here we're going to be testing whether or not this is correct by using a random sample of 69 M&Ms. And to do this, I randomly selected 69 peanut M&Ms from this bag without looking. So I would randomly select M&Ms from the bag without looking in order to avoid biases or any type of unreliable information. So now this is just basically, so this is this is the percentage or proportion that the company claims, right? So obviously, if to get our numerical expected numbers for each respective color, we get our randomly selected sample of 69 M&Ms and multiply it by the proportion of each respective color, which ends up yielding these numbers. And so this is the expected numbers for each color that one would expect to get. Now here are the M&Ms that I have, and over here is my data. So this is the observed. So from doing this randomly selected 69 samples of not 69 samples, or yeah, randomly selected 69 M&Ms, I got this data. So for brown we have 5, green 14, red 11, orange 16, yellow 10, and blue 13. And so, as I had said before, we're going to be doing a chi-square goodness of fit test for M&Ms. Now our null hypothesis is going to be what is expected, or what is already argued, or what is more already established, right? So our null hypothesis is going to be that the company's claim of the distribution cannot be proven wrong, right? Our alternative hypothesis is going to be that the company's claim is false, and that's what we're going to be trying to prove for. For purposes of this hypothesis test, we're going to set our significance level or alpha level to 5% or 0.05. So now we need to test our conditions. One, this is randomly selected. I randomly selected M&Ms from a bag, and here are the 69 M&Ms. Now we need to check for independence. Well, our sample size is 69, and if you do 69 times 10, that has to be less than the entire population of all M&Ms in the world, or that are at least manufactured by the Mars Inc. company. There has to be more than 690 peanut M&Ms manufactured by the Mars Inc. company. So yes, we can assume that these are independent of each other. That these M&Ms are independent of each other. Now to check for our large count to test whether this distribution is approximately normal, we need to have at least 5 of every, oh my bad. For large counts, our expected number of 5 needs to be at least 5 for every single type of color we have. And as we can see over here, yes, we do have an expected number of at least 5 for every single color. So for brown we have 8.62, for green we have 8.62, as so for red and yellow, and for orange we have 17.25, and blue we have 17.25. Each of those is greater than 5, so therefore we meet our large counts conditions. Therefore this distribution could be seen as approximately normal, right? So now that we have our conditions set, we can start doing the actual math behind this hypothesis. Now the first thing we need to do is calculate our chi-square, and we know that our chi-square is equal to the summation of our actual value minus our expected with this being squared divided by our expected. And we're gonna do this for every single color that we have. So let's start off with, and here's our data for reference. So over here, let's start off with brown, right? For brown, our actual value, as seen over here, was 5. So we do 5 because that's our actual value. Minus our expected. We expected a number of 8.625 squared divided by 8.625. And so we would do the same thing for red, green, orange, yellow, and blue fractions, and see what we get. So now I'm back after having done all the math, and these are all the respective values which I got for each respective color. And so now I have to remember that chi-square is the summation of all of these. So I added all of these up, and we ended up getting a chi-square of 6.8822. And so now our degrees of freedom is going to be the number of colors that we have minus 1. So in this case, we have 6 different colors that you can get. So when you subtract 1, our degree of freedom is 6 minus 1, which ends up being 5. So now to calculate our p-value, right, that we need for our hypothesis test, so you go to menu, statistics, statistics, stat test. That is the wrong stat test. Hold up. No, it's not stat test. It's distributions. So you go to statistics menu, statistics, distributions, and then you go to X or chi-square CDF. And so over here, our lower bound is going to be our chi-square statistic, which in this case was 6.8822. Our upper bound is going to be infinity, or you can put 99999, which is, we'll not use similar results. Our degree of freedom in this case is going to be 5. And we get a p-value of 0.229. So now we got our, this is the information we got. So now we got our p-value of 0.2295, right? And so what this p-value means, it's the probability that the results we obtained, given that the null hypothesis is true. And so you remember that we had set a significance level of 0.05, and since our p-value is greater than our significance level, right, we failed to reject the null hypothesis, which means that we can't say that the null hypothesis is wrong. So how we would write that is, given our p-value of 0.2295 and significance or alpha level of 0.05, and that your p-value is greater than your significance level, we do not have convincing statistical evidence to suggest that the company's claim of M&M color distribution is false.